Number 17. Performers at a play are dressed in red shirts and white pants. When blue stage light falls on them, what colors would their shirts and pants appear respectively? So this is a question about light and colors. Okay, so remember that an object will reflect the light that's the same color as itself. In the case of a white object, it will reflect any color light that is shown on it. And the case of a black object, it will absorb all of the colors. Okay, so we have blue stage light. A blue object will appear blue in white light or in blue light. And that's because white light contains blue light. Remember, white light is a combination of all the colors, okay? So you see blue when you shine blue on a blue object or white light on a blue object. Any other color light you shine on that object, it will look black because that object will absorb the color that doesn't match itself. Okay, so if we have red shirts, red will only look red if the light is red or white. In this case, the light is blue, so it will absorb the blue light and reflect no light, so it will look black. The white pants, however, will reflect white light or any other color light. White reflects everything. So white object under blue light is going to look the color of that light. It's going to look blue. Okay? So red shirts will look black and white shirts will look blue. So their shirts and pants, respectively, will be black and blue. So our answer is A. A block of glass has a critical angle of 42 degrees. Which angle of incidence must a light ray enter in order for total internal reflection to occur? So just so we know what these terms mean, okay, this one, critical angle, and this one, total internal reflection. Okay, critical angle is the angle of incidence when the angle of reflection is 90. So critical angle is the value of the angle of incidence that will give us an angle of reflection of 90 degrees, okay, which means right along the barrier. Remember that the angles are measured with respect to the normal, okay? If the angle of incidence is greater than that critical angle, then the refracted ray, okay, because this is about refraction, even though it's called total internal reflection, it means that it bends so much, it's almost like it bounced off the barrier, but it actually bent back into the barrier, okay? So if the angle of incidence, if it goes in at an angle greater than 42 degrees, then we get total internal reflection. Less than 42, we just get refraction. You'll see the angle, it will go across the barrier, but it will be bent with respect to the normal, okay? So at 30 degrees, we're gonna get just normal refraction, okay? Because it's not greater than the critical angle. At 42 degrees, we're gonna get an angle of incidence of 90. So total internal reflection has not occurred just yet, okay? It's right at the boundary line. So we still consider that refraction, okay? 60 degrees, that's greater than 42 degrees, but so is 90. So are there two correct answers? No. Let's think about what happens at 90 degrees. If we have an angle of incidence of 90 degrees, that's actually a different phenomenon. What's happening is the angle of incidence, it actually makes no angle with respect to the normal, because remember the normal is always 90 degrees to the boundary. And if we have an angle of incidence that goes right along that line, we're going to get what's called normal incidence, and we'll actually see a straight line, just going straight through the medium, through the second medium. So it will appear as if there was no bending at all, okay? So the one that we're looking for, that we're going to get that effect that looks like reflection, looks like it went in and then bounced off, is going to happen when the angle of incidence is 60 degrees, okay? All right, number 19. Which member of the electromagnetic spectrum listed below is not used for communication? Okay. Microwaves, radio waves. Microwaves might not be as obvious. They are used for more than warming up your food. Okay. Microwaves are what are used in our cell phones and our computers. Okay. So the only one that we don't use in communication, okay, and that's TV, that's radio, that's cell phones, that's computers. The only one that's not used will be are gamma rays, okay? And if you think about it, what do the other three have in common? You know, they're safe for us to use for communication because they're non-ionizing, okay? Microwaves, radio waves, visible light. We don't want to be exposed to gamma rays on a daily basis. They're dangerous. So definitely that one is out, okay? Number 20, which line in the table identifies the mode of action and origin of a sound wave, okay? Mode of action, meaning how it moves with respect to the motion of the wave, and the origin, okay, what type of disturbance causes it, okay? So mode of action, we're talking about, is it longitudinal or is it transverse? And origin causes it. Sound waves, okay, if you just put your hand on your throat as you're talking, what do you feel? Vibrations, okay? So sound waves are caused by vibrations, and they are a type of longitudinal wave, okay? Remember, longitudinal waves, they move parallel to the direction of the wave's motion, back and forth like a slinky, okay? Examples of longitudinal waves are, of course, our sound waves, P waves, earthquake waves, and transverse waves, that they are your water waves, your waves on a string, those examples, okay? When you're doing these types of questions, you want to make sure that you go through each column. Sometimes I like to do this, like, okay, I know one of the answers, so I know that this is going to be true for mode of action, and I can X those out. For origin, I'm going to cross out what's not correct and put a check next to what is, and then I'm going to look for that row that has my 2 check marks, okay? When you're checking over your work, make sure you do that, because it's easy to miss if your eye just goes right to the correct answer in only one of the columns. All right, number 21. Which motion time graph shows constant acceleration? So we have 2 types of graphs here. We have distance time graphs and we have speed time graphs, okay? DT graphs, remember, the slope of those graphs give us the speed. VT graphs, the slope of those graphs give us the acceleration, okay? Constant acceleration, okay? When you see the word constant, you're looking for, just like what I drew just now, a straight line, okay? Straight but slanted. You're not looking for a flat line. Okay, so this one here, this tells us that the speed is equal to 0. Okay, because We're not changing our distance. We're not moving. So flat lines, the slope is 0. Here, this is telling us that the slope of this graph is 0, and the slope of a speed time graph, that means that the acceleration is 0. Okay. Slanted but sloped means constant. Okay. So the slope here shows a constant value for speed. So speed is constant here. And this graph looks similar, but this is a speed time graph. So this means that the slope is telling us that the acceleration is constant. So our answer is D. Okay, so these can get confusing sometimes, but as long as you remember what the slope is for each type of graph, and you remember that flat means 0 and slanted means constant, then you should be okay. Number 22, table shows the results of 4 students climbing to the top of a wall. Which student demonstrates the greatest power? Okay, so we're talking about mechanical power here. So we're looking for this formula that relates power, work, and time. Power is equal to work divided by time. So what you're going to have to do is, yes, you're going to work out each one of those. Okay, you cannot just look at the values for work or the value for time. You need to calculate the actual ratio and then compare them, see which one is the biggest. So I'm going to tell you to pause the video now, work that out, and then come back and see if you get the same answers as me, and we'll see the correct answer. All right, so if you work them out correctly, then you would have got 250 watts for A. For B, you would have gotten 125. For C, 400 watts. And for D, 200 watts. Okay? And the greatest power is demonstrated by student C with 400 watts. All right? Number 23. A soccer player of mass 100 kilograms runs with a speed of 4 meters per second to kick a stationary ball of mass 0.4 kilograms. What is the initial momentum of the soccer player and the ball? Okay, so we want the initial momentum for the soccer player and the initial momentum for the ball. So let's look at the information we have. We know that the mass of the soccer player is 100 kilograms. We know that he had an initial speed of 4 meters per second to kick a stationary ball. That gives us some information as well. What information does that give us? Correct, that gives us the speed of the ball. Stationary means 0, okay, that it has 0 motion. It's not doing anything, so the speed is 0 meters per second. So that's the speed of the ball. I'm going to call that VB1, initial speed of the ball. And I'm going to call this V soccer player 1, and that's 4. This is the mass of the soccer player, and this is the mass of the ball. We're told is 0.4 kilograms. Okay, mass of the ball. All right, so momentum is given by the formula P for momentum, mass multiplied by velocity. So for the soccer player, his initial momentum would be his mass, 100 kilograms, multiplied by his initial speed, which was 4 meters per second, which would give us 400 kilogram meters per second. The ball was stationary, and if we plug in the numbers there, we should already know that if an object is not moving, then it has no momentum. And if you plug that in your calculator, you will see, of course, the ball with a mass of 0.4 kilograms has no velocity, 0 velocity, 0 times anything is 0, so 0 kilogram meters per second. So we're looking for the column that has the correct answer for both of those. So we're going to do our little check method here. So we're looking for 400 kilogram meters per second for the soccer player. So that's correct, that's correct. This is not. And 0 for the ball. That's correct, that's correct. This is not. Where are 2 check marks? B. Right there. Okay? Good. Number 24. Convex mirrors are commonly used in everyday life. Which row describes a convex mirror? Convex mirrors have a surface that curves out, like it bulges out, okay? And what it does when light strikes it, it spreads the light out. Another word for spreads out is diverges, okay? One example of this are the mirrors that you see in a store in the corners that allows the cashier to see a wide view of the store at all times. Okay, this is also the type of mirror that you will find in the passenger side of a car that allows you to see way behind you and on the side of you when you're driving, so you can know when cars are close to you. So we're looking for diverges light and produces a wide field view. Okay, that would be C. Number 25. A common eye defect is shown in the diagram. Which row shows the eye defect and its corrective lens? All right, so we see that this point here, this is where the image will form. And this the back part of the eyeball is where our retina is. And that's like the screen where your image is supposed to form. But as you can see, it forms behind the retina here. So the light has spread out too much, spread too far, and we don't get a clear image because it's not right there on the screen. It's spread out too far. So we need the type of lens to pull the light together to make it come together. What does that sound like? We need a converging lens, okay? And another name for a converging lens is a convex lens. This is called farsightedness, okay? The image is formed too far behind the retina, okay? And as you could probably guess now, nearsightedness is when it's too close. The image is formed before it reaches the retina, okay? So remember that difference. So this is farsightedness, okay? And we need the lens that has the opposite effect, okay? So if the light is too spread out, we need the type of lens that brings them together. So that'll be a convex lens. So our answer is B. Okay, so let's just write that down so we can remember. Near sight, image before retina, far sight, image after retina, retina. Okay, I'm having my own jokes here. All right, moving on. 26. Candace directs a ray of light at a plane mirror as shown in the diagram and observes its reflection. What is the angle of reflection? Okay, don't get tripped up on these. Remember that the angles are measured from ray to normal, okay, between the ray and the normal, not from the boundary. All right, but this does help us out because if we know anything about angles at a point, we know that if we have a right angle, the total amount of degrees that we will count from there to the boundary is going to be 90 degrees. So if we know this part, we know this is 25, then this is going to be 90 minus 25, which is going to give us 65. And what do we ask for? That's not the only thing that we need to look for. So if we know this angle, then we have to, is this good enough? Are we done? What do we ask for? We're asked for the angle of reflection, okay? So this here that we've just found is actually the angle of incidence, okay? It's the angle between the incident ray, you see that one's going into the boundary, and then this one here is going out. So this is our reflected ray. The angle of reflection, as we know from our law of reflection, is equal to the angle of incidence. So if that is 65 degrees, then so is this one, okay? So our answer is B. Number 27, which is a magnetically hard metal? Aluminum, iron, steel, or zinc? Okay, hard metal means that it is difficult to magnetize, but retains its magnetic properties longer. Okay, well, right off the top, we know we're going to cross out aluminum and zinc because those are not magnetic materials. So it's between iron and steel. Okay, our soft magnetic material is iron. That's what we use to make electromagnets. We know we want to be able to turn them off and on very easily. So that one is out. Our hard magnetic material is steel. Okay, where do we use those? Motors. We would use hard magnetic materials for because we want them to stay magnetized so they can continue producing motion. Okay. Number 28, a student investigates the magnetic fields around wires carrying current using iron filings and plotting compasses. Two of the magnetic fields obtained are shown. Which row correctly classifies magnetic fields A and B? All right, there are a couple of things that we need to look for. Remember, a magnetic field is a vector quantity, so we need to look at the direction of the field, okay? And then we're going to be applying the right hand grip rule to determine two things. We need to know the direction of the current along the wire, and we need to know the direction of the field, okay? So the right hand grip rule says that if you grip a wire with your right hand and your thumb points in the direction of the current, then your fingers curl in the direction of the magnetic field. Okay? So let's check out these the direction of the field, first of all. It's concentric circles. That's characteristic of straight wires, okay? So that's the first thing that we can rule out. So anything here not talking about straight wires, then we can X those out. This is not the magnetic field of a circular coil. The magnetic field of a coil looks like two sets of concentric circles with very straight field lines in between them. Okay, it looks like, you know, like two eyes and a nose. So circular coil, out. Okay, so we've already eliminated 3 options just based off of knowing the shape of the field. Now let's make sure that we're absolutely correct by investigating the direction and make sure that it matches our answer, okay? So carrying current into the wire, these diagrams in the middle, the cross and the dot, are drawn to show what you would be seeing if you were standing in front of the wire. So let's say they represent arrows, okay? So if you are, we're trying to denote coming out of the paper, like towards you, then you would see a dot, okay? Apply your right hand grip rule now, and I want you to curl your fingers around the field with your thumb pointing toward you. Okay, that's coming out of the page. And you'll see that your fingers curl in an anti-clockwise direction. Okay, same hand. Now rotate your hand so that your thumb is pointing away from you. You're pointing into the page now, into the paper. And you'll find that your thumbs curl in the opposite direction. They curl in the clockwise direction, okay? That's what those diagrams are saying. And we find that D matches both of those descriptions. We knew that because we had to cancel out some options already. So our correct answer is D, okay? But you want to keep those in mind. So cross is into, dot is out of, okay? All right, let's take a break there.